right. So this is, I think, problem set 10. And this homework is a tricky one because it is on related rates, which is a pretty difficult topic in my opinion. But let's just jump into number 1 and see if we can figure it out. So it says, suppose a spherical balloon is deflating so that the radius shrinks at 4 inches per hour. And the first question is, what is the value of dr dt when the radius is 2? So dr dt is the rate of change of the radius. And that's actually already given to us pretty clearly because it tells us that the radius shrinks at 4 inches per hour, which means that the rate at which the radius is changing is a negative 4 inches per hour. So that's our answer right there. It's just negative 4. And you could write your units of inches per hour, but it is just a constant. It is negative 4. Now part B says, what is the rate of change of the surface area S when the radius is 2? Well, this requires us to know the formula for the surface area of a sphere, which I would recommend just having a little cheat sheet of this so you don't have to look it up every time, because frankly it's not something that I have memorized typically. But the surface area, I'm just going to write that as S, like they called it, of a sphere is 4 times pi times the radius squared. So what we want to do here is we want to figure out the derivative of the surface area with respect to t, because that is what the rate of change of the surface area will be. So if we take the derivative with respect to t, so it's going to be ds dt equals whatever the derivative of this is with respect to t. So this is technically an implicit differentiation. So I know 4 and pi are constants. This is a constant coefficient here. So I just have this variable here. I know the derivative of r squared is 2r. And since this is with respect to t, I'm going to also multiply that by dr dt. And I'm just going to rewrite that for convenience sake. Sorry, forgot the word. So I'm just going to put that 2 and combine it with the 4. So 2 times 4 is 8. So it's 8 pi r dr dt. Well, we just found out that when the radius is 2, dr dt is negative 4. So we can actually plug that back in. So ds dt equals 8 pi r times negative 4, or just negative 32 pi r. And in this case, the radius is 2, so we can plug that in as well. So it's just going to be negative 64 pi is our answer there. And if you wanted the decimal version of that, you can just type in 64 times pi into your calculator, and it'll give you the big long decimal that forms from multiplying by pi. But we don't need that right now. So let's move on down to part C. It says, what is the rate of change of the volume when the radius is s? Well, if you remember, it's a spherical balloon, so we have to know our formula for the volume of a sphere, which the volume of a sphere, we'll write as v, is 4/3 times pi r cubed. Oh, and I actually have it written down here. Fun. It's a little note for us. So we wouldn't want to figure out the rate of change of the volume, which is going to be the derivative of volume with respect to time. So dv dt. So if I take this derivative just like we did with our surface area, we get dv dt equals, it's going to be 4/3 times pi times the derivative of this with respect to t, which is, use our power rule, it's going to be 3r squared, and then because it's with respect to t, dr dt. Right? So I see that if I do move this 3 in front, I'm going to get 3 times 4/3, which actually, obviously 3 times 4/3, my 3's are going to cancel. So I can rewrite this as 4 times pi times r squared dr dt. And once again, we found that when the radius is 2, dr dt is -4. So I'm going to plug that in, as well as our r value, which we know is 2. So our radius is 2, so it's 2 squared, times our dr dt is -4. So that's going to be 4 pi times, well, 2 squared is 4, times -4, which is just going to be, that's going to be 16, -64 pi, which is really funny that that actually worked out to be just about the same as the rate of change of our surface area. That's just a funny coincidence. That will not always be the case. That's just how that worked out here. That's fun. But yeah, that's all that that problem's looking for. I know that our implicit derivatives can be confusing at times. How did that work? It can be confusing at times. But yeah, if we're taking the derivative of something and we have a variable that is not in terms of the derivative we're taking it in. So if I have, if we had v equals this right here, and I'm taking the derivative with respect to t, well, I've got this variable r, which is not t, so when I take that derivative, I have to use my dr dt. If I was taking the derivative with respect to r, that would be dv dr, and then I don't need to do that. So then I would do 4/3 times 3 is 4 pi r squared. And I don't have to write a dr dt because that's dr, which is just 1, right? Because it's it with respect to that variable. You don't have to worry a whole lot about that explanation if you already think you understand implicit derivatives, or if that confused you more, please ignore it. But hopefully that helps a little bit. Moving on to number 2. Again, we have a spherical balloon, but this time it's inflating, so it's getting bigger, such that after t seconds, its volume V is given by this equation here. And remember that the volume of a sphere is always going to be this right here. So what we found is that they have this, and we know that those are obviously going to be equal to each other because they're both the volume of a sphere. This one's just the volume of this particular sphere at a point in time. So the very first question is, after 64 seconds, the radius of the balloon is what? Well, we're given nothing about the radius. All we're given is the equation for the volume. So since we know the volume of a sphere is also this over here, I'm just going to set those equal to each other and see where that gets us. So, and I can do this because they're both V, right? They're both the volume of a sphere. So in this case, we're looking for what R is. So we're solving this for R. I see we've got an R in there, so that makes it pretty easy for us. So all I have to do is just isolate my R variable. So I'm going to go ahead and undo multiplying by 4/3. I'm going to divide by 4/3. So, or rather, I'm going to multiply both sides by 3 to cancel that out, which gets me 6 times the cube root of t equals 4 pi r cubed. And now I can divide by 4. So 6 over 4, and that's going to reduce actually to a 3/2 equals pi r cubed. So then I'm also dividing by pi, and I'm just going to flip this around, so don't be alarmed by that, just so that it's easier for me to read personally. So same thing happening, except now there's a pi in our denominator because we're dividing by that as well. Now I've got r cubed equals this. And that's all fine and dandy, but we want to know what r is. So r is obviously going to be the cube root of all of this here, which is pretty ugly, I know. Thank God for calculators. I mean, I suppose we could leave it in terms like this, but yeah, I would use a calculator here. But, so it's after 64 seconds. So 64 is our t value. So it's going to be 3 times the cube root of 64 over 2 pi. Well, the cube root of 64, I know off the top of my head, is 4, right? Because 4 times 4 is 16 times another 4 is 64. So that's going to be the cube root of 12 over 2 pi, because 4 times 3 is 12. We can reduce that even further to the cube root of 6 over pi. And that's as far as we can reduce that. So our radius at 64 seconds, we just found, r equals the cube root of 6 over pi in this case. And I personally would type that into a calculator just because I don't always know what the homework will accept in terms of formatting. And I would just write out that entire decimal for our web assign. But for, like, if we have a question like this on the exam, you absolutely can leave it in terms like this, especially since I don't believe we're allowed calculators on our exams. So that is the radius there, and I hope that that made sense. I know I went through that a little quickly. And now it's asking how fast is the radius changing after 64 seconds. So we need to do all of this again, except we need to take the derivative so that we can get dr dt to solve for. And I could just take the derivative of this, but that's pretty ugly given the multiple cube roots and the fraction within it. So I'm actually going to go back to our first equation, just because that's a little easier to work with. Remember where I set our volumes equal to each other, and I'm actually just going to rewrite that once it lets me erase this. Okay, so I'm going to rewrite that. I'm going to set our volume formulas equal to each other. So they gave us v equals 2 times the cube root of t. And we know the volume of a sphere is 4/3 times pi times r cubed. And now this is a lot easier for me to take the derivative with. So I'm going to go ahead and take the derivative of all of this with respect to t. So in this case, I'm actually going to rewrite that right there as t to the 1/3 power, just because that way we can use our power rule and we don't have to worry about anything complicated with that derivative. So take the derivative of this side. Well, it's going to be 2 times 1/3, because I bring my power in front, times t, and I subtract 1. It's going to be to the negative 2/3 power, equals, and we take the derivative of this side, so I get 4/3 times pi times 3r squared dr dt. Remember, because this is with respect to t. And yeah, and again, I see that these 3's are going to cancel out, so I'm going to rewrite that. Got 3 times t to the negative 2/3 equals, I see my 3's cancel, so I've just got 4 pi r squared dr dt. Well, now we just have to solve for dr dt. So I just have to divide this by this. And I'm actually going to go back and rewrite this t right here with my radical again, just because personally that's easier for me to read. So first, just so I don't lose anybody here, it's going to be 2/3 times 1 over t to the 2/3, right? To get rid of the negative in that exponent, which then turns into 2/3, or rather 2 over 3t to the 2/3, which is then also just 2 over 3 times the cube root of t squared, because our exponents are fun that way. And of course, all of this is equal to this right over here, dr dt. Just kind of carry that down because it's all equal there as well. And again, we're solving for dr dt, so I'm going to divide this by this, which means that this chunk here is going to move into my denominator. So I get dr dt equals this. Divided by this, so it moves into my denominator. And I see I've got 2 constant coefficients there, so I'm just going to rewrite that to combine them. So I get 2 over 12, I should write the pi in front. Cube root of t squared times r squared. And I can actually cancel that. It's always just nicest to simplify and reduce as much as possible. And I'm actually going to move my r squared in front so it doesn't get confused with the radical at all. And then, boom. So now we know that dr dt, I'm actually going to write that a little higher. So dr dt equals what we just found, which is all of this underneath a 1. But we obviously can't put that in because we've still got variables involved. So we have to plug in 64 for our t, because it's after 64 seconds. We also have to plug in our radius, which we actually found a numerical value for our radius. So we're going to plug both of those in here. First of all, if I have the cube root of 64 squared, well, the cube root of 64 is 4. 4 squared is 16. So this bit right there turns into a 16. I'm just going to make note of that. So it's going to be 1 over 6 pi times this squared. So I'm going to rewrite that times 16, because that equals 16. And again, we'll just kind of combine things. Let's see. 16 times 6 is... It's not... No, okay. So that's 60 plus 36 is going to be 96. So it's going to be 1 over 96 times the cube root of 6 over pi squared. Or I suppose, just so we don't have a radical there, I'm going to rewrite that with exponents, which that's the same thing. Oh, I left out our pi. I'm actually going to, because remember there's the pi there, times that. I could rationalize this, but frankly, I don't feel like it. So I'm just going to leave this as our answer. Again, I would personally type this into a calculator for the homework, just to figure out exactly what all that is. But yeah, if we have a problem like this on the exam, and we can't use a calculator, leave it in terms like this, as ugly as it is. Next up, actually I'm going to erase some of this. Give me a moment. Okay. Just so we've got uninhibited space. It says a small spill produces a circular puddle with an area that increases at a rate of 7 square millimeters per minute. How fast is the radius of the pool increasing when the radius equals 20 millimeters? Well, they tell us that it's a circular pool, and that it has an area that increases at a rate of 7 square millimeters per minute, which means that they just told us the rate of change of the area is 7. Okay, so the derivative of area with respect to t, or the rate of change of our area, is 7. It's increasing, so it's a positive 7. 7 square millimeters per minute, but I'm just going to write 7. Now, I want to know how fast is the radius of the pool increasing when the radius is 20 millimeters. Well, I know that the area of a circle, because this is a circular puddle, I know the area of a circle is pi r squared. So I can solve for dA dt by taking the derivative with respect to t, which is going to be 2 pi r dr dt, because I just took that implicit derivative, right? Derivative of r squared is 2r. I just moved the 2 in front, and then dr dt, because it's with respect to t. So these are two equations now for the derivative of a with respect to t. So once again, we're going to set them equal, which we can do because they're representing the same thing, so they should be equal. And now we're going to solve for dr dt. So I see that this is all multiplying, so if I want dr dt by itself, I'm just going to take this chunk and divide it out. So I'm going to divide all of that by 2 pi r, divide that by 2 pi r. So 7 over 2 pi r equals dr dt. And we're told that the radius is 20 millimeters at this point. So I'm going to plug that in there. That's going to be 2 pi times 20. So dr dt, as I rewrite it over here, is going to be 7 over 2 times 20 is 40 pi. 7 over 40 pi. Ta-da! That was one of the easier ones. Now, number 4 says a point moves around an ellipse given by this equation here. And when the point is at this coordinate, its x-coordinate is decreasing at a rate of 5 units per second. The first question is asking us whether or not the point is moving clockwise or counterclockwise. Well, I think that it's easier personally to kind of draw this out. So if I just sketch a little coordinate plane, I know that the center should be at 0, 0, I believe, if I remember how ellipses work. And the x-axis goes 1, 2, 3, 4, 3, 4, goes out to here. That's our major axis, and our minor axis is our y-axis in this case. So I'm just gonna gently sketch this out, and we're gonna get an ellipse, something like this. Oh man, that's a potato. That's okay. It's gonna be something like that. You get the gist. And so at the particular point they gave us, so at 1.9, so it's about there, 1.9 comma 2.64. I'm gonna mark that in red. Okay, so at that point, the x-coordinate is decreasing at a rate of 5 units per second, meaning that the x-coordinate is going that way. It's going into the negatives because it's decreasing. So it's moving leftward. In this case, that tells us that it's moving this way along our ellipse, which shows us it's going counterclockwise in this case. Which is why I think that the picture helps. Now, with our actual derivative, we want to figure out if the derivative of this function, dy dx, is greater than or less than 0. So I'm just going to go ahead and take the derivative. So 5x squared over 16 plus y squared over 9 equals 1. If I take that derivative implicitly, well, this is just 1/16 times x squared plus 1/9 times y squared. Just remember that those are constant coefficients. Don't get yourself confused and think we need a quotient rule or anything. And so now, well, the derivative of x squared is 2x, so I get 2 over 16, or just 1/8 x. This is with respect to x, so I don't need anything there. Plus the derivative of y is going to be 2y dy dx, so 2/9 y dy dx equals, and the derivative of 1 is 0 because it is a constant. So now I want to get my dy dx all by itself, so I'm going to move this over. I'm going to subtract this from both sides. So I get 2, and I'm actually going to move the y up into that fraction there because they're multiplying. I can do that. Equals negative 1/8 x. And now to get dy dx all by itself, I just divide by this. And I know that this looks awfully ugly, and I'm going to bring it up here for space. Negative 1/8x divided by 2y over 9. Remember that when we're dividing by a fraction, it's the same as multiplying by the reciprocal. Sorry about that. Yeah, so when we're dividing by a fraction, it's the same as multiplying by the reciprocal. So this is the same as negative 1/8 1/8 x, which I can just write as negative x over 8, right? Because 1 times x is 8. Again, I could just rewrite it as division like that, which is the same as multiplying by our reciprocal, which is going to get me negative 9x over 16y. So what we just found was that dy dx equals negative 9x over 16y. Which means that at this point, since our x and y are both positive and this has a negative, I know that the result of this plugging this in is going to be negative and therefore less than 0. You can double check that just by plugging them in. It should be exactly that. Don't know what that was. And then letter C, it says how fast is its y coordinate changing at that instant? So we want to know what dy dt is. We want to know the rate of change of y with respect to time. So if dy dx is this, and we want to find dy dt, well, we can go back to our original equation, which we see I rewrote here. So we're going to use this rewritten version here, just so that I don't have to rewrite it again. And we're going to take that derivative again, but this time with respect to t instead of x. So again, the derivative of x squared is going to be 2x, so I get 1/8 times x, except now it's with respect to t, so it's also dx dt. And then plus, let's see, it's 1/9. We remember our derivative of y squared was 2y, so it's 2/9 y dy dt equals 0. And again, we're just solving for dy dt. So it's the same deal. So this is x over 8 dx dt. And I'm going to subtract that from both sides. Oops. So that I can get only my term with dy dt on this side. I'm going to move up here. Oops, I didn't erase that. So I'm going to get 2/9 y, or again, I'm going to write the y in the numerator there. Dy dt equals negative x over 8 dx dt. So if I want to find dy dt, I divide by all this. So that's going to be dy dt equals negative x over 8 times dx dt, all divided by 2y over 9. Again, it's the same as multiplying by the reciprocal. In this case, I'm just going to kind of ignore my dx dt and multiply that with this. So it's going to be, again, negative 9x over 8 times 2 is 16, cy, all times dx dt. And now you're probably wondering, what the heck is dx dt? Well, that's the rate of change of x with respect to time. So it's how fast the x coordinate is changing, which they actually tell us already. Our x coordinate is decreasing at a rate of 5 units per second. So they just told us that our dx dt is a negative 5. Because remember, it's decreasing, so we have to use that negative, which means that all of this is times negative 5, which makes dy dt, because remember that's what all of this is equal to. Let's kind of carry that down. Dy dt is equal to, well, negative 9 times negative 5, 45x over 16y. Okay. So now the only trick is that it wants to know exactly how fast the y coordinate is changing at that point. And we did figure out what dy dt is, but we don't know what dy dt is at that point yet. So all we have to do to figure that out is take our x and y value that they gave us for that coordinate and plug it in. So in this case, it's going to be 45 times 1.9 over whatever 16 times 2.64 is. And yeah, you just multiply that out with a calculator. But I'm just going to leave it like that because my wrist is hurting. And we've got like 4 more questions to do still. So next up, it says a 13-foot ladder is sliding down a wall, which you could picture as, let's call this our wall, right? And I've got this ladder here. My 13-foot ladder is sliding down a wall. Figure not drawn to scale because this doesn't quite match the question. It says at this moment, the bottom is 12 feet from the wall. So I'm going to call that x and say x is 12 feet. And the other end is moving along the wall at a rate of -3 feet per second. So this end here we'll call y, and we don't know what y is. All we know is that the rate of change of that with respect to time is -3, right? Because that is moving on the wall at -3 feet per second. So the first question is, how fast is the bottom end sliding across the ground? Well, that means that we want to find what dx dt is. That's what we're looking for. And the first thing I see is that this forms a right triangle where we don't know one of our sides. So I'm going to just use my Pythagorean theorem here. I'm going to say x squared plus y squared equals, in this case, c squared is 13 squared. So it's going to be 12 squared, which is 144 in this case, plus y squared equals 169. And actually notice this is one of our special right triangles. It's one of our Pythagorean triples. And y is going to end up being, we're just going to make a note of it down here, y is 5. Now that we've solved for y, because that's not what it's actually asking us, we've got this equation here that we know is true about this triangle. Well, if we want to find what dx dt is, well, I've got an x right here, so why don't I just implicitly derive this? Well, let's try it. So we're taking it with respect to t, so it's going to be 2x dx dt, right, plus 2y dy dt equals, and well, 13 squared is just 169, and the derivative of that is 0 because it is a constant. So this is what we've got here. And luckily for us, we have very few unknowns. We know our x, we know our y now, we know our dy dt, we only don't know dx dt, which is what we're solving for, so that's perfect. So let's go ahead and just solve the equation in terms of x and y. So it's going to be it's going to be 2x dx dt equals, I'm going to subtract this from both sides. It's going to be equals -2y dy dt. And then to get dx dt by itself, I divide by 2x. So dx dt equals -2y. And remember, dy dt we know is -3 over 2x. I see my 2's cancel. So this just turns into, and I know my negatives cancel, this turns into 3y over x. So if the rate of change at the bottom is 3y over x, we know y is 5, so it's 3 times 5 is 15, over x is 12. The bottom end is sliding across the ground that way at a rate of 15/12 feet per second. Or I could rewrite that as, I believe, 1 3/12 or 1 1/4 of a foot. Next up, it asks, how fast is the area of the formed triangle changing? Well, so that's asking us about this area right in here. And we know that the area of a triangle is 1/2 times the base times the height. In this case, our base is our x and our height is our y, right? That makes sense. So I'm going to rewrite this in terms of x and y. I'm going to write area is 1/2 x times y. And we're looking for how fast the area is changing, which means we want the rate of change of the area with respect to time, or dA dt. So I'm going to take the derivative of this. Well, I know it's going to be 1/2 times whatever the derivative of x times y is. Well, I need to use product rule here, because it's an x times a y. Remember that product rule says we have our first value times the derivative of our second, plus the derivative of our first value times the second. So I'm going to have x times the derivative of y, which is just 1 times dy dt, plus derivative of our first one, so it's going to be 1 times dx dt, times our second, which is y. Which, obviously we don't want it in terms of x, y, dx dt, and dy dt, but we know all of those values now. We've solved for all of those. So I just plug those back in. So it's 1/2 times our x was 12. Our dy dt they gave us was -3. Dx dt we found was 15/12. And y we found was 5. So we just go through these motions here. So it's going to be 1/2 times the -36 plus, 15 times 5 is 75 over 12. And I'm going to go ahead and distribute that half actually. So 1/2 of -36 is -18 plus, and that's going to be 1/2 of this, which is going to be 75 over 24. And it's a little ugly because we've got some bigger numbers than I'd hoped. Oops, did not mean to do that. So we've got dA dt equals whatever this turns out to be, which looks like it's a negative number. So the area is decreasing. I can actually reduce that. So 75 24ths. I know I can reduce by at least 3, so it's going to be 25 over 8. Yeah, and that's a little easier to work with. So I'm going to actually just rewrite that in here. So 25 over 8. Okay, so now I've got a -18 plus 25/8. What is 25/8 as a mixed number? That's going to be 3 and 1/8. So it's going to be a -15, -14, and 7/8. There we go. Sorry, that was not intuitive for me. So that is our answer. It is changing at a rate of -14 and 7/8 square feet per second. Number 6 isn't on related rates at all. This is just some more chain rule practice, and I was considering omitting it, but I figured it's good to practice chain rule because it's a pretty tricky one to remember sometimes. You'll notice that I am omitting the limits problem from the homework just because that is a pretty early problem that we've done on, I think, multiple homeworks by now. So if you're struggling with that, it's definitely addressed in one of my other videos, and I'll see if I can find it and link it in the description with the right time if you're stuck on that. Otherwise, I would go reference any old homeworks that include it. But for this one, we've got y equals 3 times the natural log of sine of e to the power of 3 times t. And we want to figure out what dy dt is, so we're going to take the derivative of y with respect to t. We're taking the derivative of all of this with respect to t, and I'm just going to erase all that to make some space. So it's going to be, since y equals that, oops, it won't write. There we go. Oops, what? I don't know how it did that. It's lagging so much. My computer isn't lagging, it's just the whiteboard program. But anyway, so it's going to be dy dt, right, because it's with respect to t, equals whatever the derivative of all of this is with respect to t. And I can see that I've got an outside and an inside and an outside and an inside and an outside and an inside. So we're going to use our chain rule to just kind of set this up elsewhere. So I'm going to say my u is 3 times the natural log of my first inside My first inside is also an outside. So it's going to be sine of my next inside. My next inside is again also an outside, so it's e to the power of, and I'll use an L, a cursive L. And then L is our final inside. It is not an outside, it's just 3t. Now I know the derivative of, natural log of x is just 1 over x. So I know the derivative of natural log of v using chain rule is going to be 1 over v times the derivative of v, which I could just write as the derivative of v over v, but I've got a 3 here, so I have to multiply it by that. And yeah, so that's going to be that first derivative. The derivative of v now, I know the derivative of sine is cosine, and because chain rule, we multiply by the derivative of our inside, which is c. The derivative of our inside, well, the derivative of e to the power of anything is itself. Just give me that, times the derivative of our inside is that, and then the derivative of our inside is just 3, right? Because the derivative of 3t is 3. So now I plug all that back in. So I've got e to the power of L is 3t, times L prime, which is 3. Now I plug that up in here, because that's our c prime, which is 3 e to the 3t. I just moved this in front, so don't get lost there, times cosine of c. C was e to the 3t. And then plug all of this back in for v prime, which is going to be 3 times 3 e 3t cosine e to 3t all over whatever v was. V was sine of e to the 3t. Right, because it's a sine of c. C is e to the power of L, and L is this, so I just plug those all back into each other. And that is our derivative. I don't believe I lost anything. So I'm just going to rewrite that over there. I know 3 times 3 is 9. So 9 e to 3t cosine e to 3t all over sine of e to 3t. And we'll notice that they actually have a coefficient times an e in front of the fraction. And really that's no different than what we have here. This is just multiplied by that. I could take it out of the fraction technically because it's just multiplication. So I can rewrite that as dy dt equals 9 e to the 3t times then this right here. And while it's not relevant to this per se, but it's worth noting that this right here is cotangent of e to the 3t, right? Because cosine over sine. But that's not something we need to worry about right now. So I see my coefficient is 9, and I've got e to the power of 3t times cosine to the power of 1 of e to the 3t over sine to the power of 1 over e to the 3t. All right, and now into the tougher ones. These last two are mostly just a lot of work. Number 7 says a conical cup, or a cone-shaped cup, is being filled with water at a rate of 2/5 cubic inches per second. If the cup is 8 inches tall and the top has a radius of 5 inches, how fast is the water level rising when the water is 2 inches deep? So what that tells us is we've got a cone that looks maybe something like this, right? It says it has a radius of 5 inches and the whole thing has a height of 8 inches. Okay. We want to know how fast is the water level rising when we have this bit here of our h, and our h is 2 inches deep. Okay. Well, I know off the top of my head, no I don't, I have it written down that the volume of a cone is 1/3 pi r squared times the height. So it's 1/3 times pi times the radius squared times the height. So the volume of this whole thing would be if I plugged in 5 for my radius and 8 for my height, but that's not what we're looking for. We want to know how fast the water level is rising. So we want to know how fast this height is changing here, right? So we want to know what dh dt is, which means we need to take the derivative of this. We have dv dt. And they actually gave us that at the beginning. It says the conical cup is being filled with water at a rate of 2/5 cubic inches per second. If you weren't sure, that cubic inches is a key giveaway that we're working with volume. So that actually tells us that the rate of change of the volume is 2/5. It's increasing at a rate of 2/5. So I'm just going to make that a little note up there. But we're going to find our own dv dt by taking this derivative implicitly. Oh, that rhymed. So again, these are constant. These are variables. So I'm going to take, that's going to be 2r. So I'm going to 2/3 times pi times r dr dt times derivative of h is just dh dt. And now we might feel pretty stuck because we don't know what any of these are. We don't know any of these values. So what we have to do is we have to recognize that when we have this cone, and we have our height and our radius, we're forming a triangle here. So we're forming this triangle where that's 8 by 5, right? And inside of our cone is going to form a similar triangle, where in this case it is our h and our radius. Okay. And so in this case, we want to find what dh dt is. So we need to figure out either h or r in terms of one another. So when the radius is 5, h is 8. When the height is 8, the radius is 5. Which is tricky to process, and I'm blanking. I'm so sorry. I had it and I'm blanking. Which means that the ratio between the two is something. There is a ratio. That's the bit that I remember. Oh man, I am really blanking. It's evening. Let's see. So let's say h equals, well, r would be 5. No. No. Does that make sense? Yes. So h would be 8/5 of r, and r would be 5/8 of h, right? And I can double check that by plugging them in. When my radius is 5, well, that's 8/5 times 5. Those cancel. When my radius is 5, is my height h? Is what? Is my height 8? Yes. Sorry, I've had a long day. And vice versa. When my height is 8, is my radius 5? Yes. So I could use either of these, coming back to this, to figure that out. And I'm actually going to replace my r with this. And we're going to do that before we take the derivative, actually. That is a point I forgot. Because if I plug it in after I take the derivative, I still don't know what dr dt is. And it's just not super helpful. So I'm going to rewrite this as 1/3 pi, and our r is 5/8 of h squared times h. And of course, these are going to be combined. So let's see, 5/8 squared is going to be 25/64. So if I have 5/8 h squared is going to be this, and then times h. I rewrite this like so. H cubed, right? Because I've got an h squared times an h, so it's h cubed. Probably for the best that I combine that. So I'm gonna rewrite that bit. Sorry for erasing those ratios. You can always rewind if you forgot them. So I'm gonna just rewrite it up here, our v, I'm just moving up. It's gonna be, let's see, 3 times 64 is it 192 or 196? I think it's 192. It's gonna be 25 for 192 pi times h cubed. Now if I take the derivative of our volume with respect to t, I've just got this times the derivative of this. So it's 25 over 192 times pi times 3h squared dh dt. Remember, dh dt is what we're looking for. We just multiplied by 1/3, so that 3 is actually going to undo that bit. It's going to cancel out, so it's going to be just 25 over 64 again, right, because that cancels out a little bit. H squared dh dt. And you might be thinking, well, we don't know what dv dt is, but remember, they gave us that, right? dv dt is the 2/5, so we're going to plug that back in. So I'm going to rewrite it over here. 2/5 equals 25 64ths pi times h squared, and our h at this point is 2. So 2 squared is 4, all times dh dt. Well, if I do that, that's going to be my 4 times this. I know that's going to turn into 2/5 equals 25 over 16, I think that should be, pi dh dt, and then I just divide both sides by that. So I'm going to get 2 times 16 is 32 over 25 times 5 is 125, and then pi equals dh dt. I know that was a lot of steps, and I know I blanked and probably wasn't explaining the best, but I hope that that made sense. Feel free to rewind, or to Google, or to look in the textbook, because there's an example that kind of walks you through it. Although I don't know that they walk through the exact same way I did. But anyway, we found that the rate of change of the height of the water is this, and we know that that's going to be in inches per second. And that's the answer. That's how fast the water level is rising. Okay, now finally, and I'm going to go ahead and erase a bunch of that because we need space for this one to really draw it out. This is a tricky one. It says a water trough, like the ones that pigs get, is 10 feet long, and its short faces each form an equilateral triangle with sides 3 feet long. So what that looks like, if I kind of draw it out, it's going to be a little water trough, and I'm going to get my short faces are triangles. I should draw that at a slightly different angle. My short faces are triangles. Just like that, with sides 3 feet long on each way, and the whole thing, oops, it's a little easier to do on paper, is 10 feet long. Okay, so that's our little water trough. Let's say we've got water in it. We know that the water fills the trough at a rate of 6 cubic feet per second, which means that the volume is increasing at a rate of 6 cubic feet per second. So dv dt equals 6. Again, just going to make a little note of that. And it asks us, how fast is the water level rising when the depth of the water is 3/4 of a foot? Okay, so our height, we can actually find it right over here. Our water level is going to be shown on that face, right? So we want to think about our triangle. Again, we're going to use H, which means that we're looking for DHGT. And the first thing they ask us, actually, to help us get to that answer is, what is the height H of an equilateral triangle of side length S? We want to keep that in terms of S. So if you've got this equilateral triangle, that means all of our sides are the same. We know our height is H. So if I want to figure out the height, I can use Pythagorean theorem. So now that I've just cut this in half, which means that the triangle I just formed right here with H and S up here is going to be 1/2 whatever that S was, right? Because I cut it in half. So if I want to find our H, well, I know H squared plus this equals this, right? Because this is my hypotenuse, these are my legs. So I'll use the Pythagorean theorem. H squared plus 1/4 S squared equals S squared, and I want it in terms of S. So I'm going to subtract 1/4 S squared from each side, which is going to get me 3/4 S squared. And then if I want H, of course we take the square root. So H is going to be the square root of 3/4. And actually, if I have an S squared inside my radical, I can pull it out. So it's going to be S, because the square root of S squared is S, obviously, times the square root of 3/4. Right? Because I went from there to there. Which does help us, I promise. We know that the volume of something, or V, is essentially the area of the face times the height, I believe. No, times the length. Oh, it's difficult to remember the terms. Times something else. Let me just get out my notebook really quickly, just to double check so that I can remember exactly what it was. Aha. So it is the length times the area. Why did I not write this clearly? Yeah, no, it's just that. It's the area times the length, right? So it's the area of whatever face is formed times the length of the whole thing. In this case, we know that the area of the face is going to be a triangle, and we know that the area of a triangle is 1/2 base times height. Well, we want it in terms of H because we're looking for DHGT. So I want my base, which is going to be an S, obviously, because it's our equilateral triangle, to be in terms of H. So I'm going to actually take this, and I'm going to go the other way. I know I'm going to undo this, so I'm going to get 4/3 H squared equals S squared, right? And then S equals the square root of that, so it's going to be H times that. Now, if I want the area, that's going to be 1/2 S times H, which turns into 1/2 this times H, or 1/2 H squared, square root of 4/3. That's our area. And our length is obviously 10 feet, so our volume becomes 10 times 1/2 H squared times square root of 4/3, and I could simplify that to 5, because 10 times 1/2 is 5. Okay, so this is our new volume equation, and I know there's a lot of steps to this, but it will work itself out, I promise, as long as we just keep on going, and just keep looking for how we can find any unknowns and work it out. So if this is our volume, we know we're looking for it when H equals 3/4 of a foot. We're looking for DH dt when H is this. And we know that dv dt is, I believe, 6 was what it was. Yeah, it was 6. So if I take the derivative of this to find our dv dt, well, this is a constant times a variable. So the derivative of h is going to be, so it's 2 times 5 is 10. And I'm just going to move this in front times that times h, right? Because I subtracted 1 from my exponent, times dh dt. Now, I want to set these equal because we know what dv dt is. So it's going to be 6, right? Because I'm plugging that in. Equals 10 times 4, square root of 4/3, times, remember h is 3/4 at this point, times dh dt, which stays unknown because that's what we're looking for. And you'll notice that everything else is now constants. We just have to solve for what dh dt actually is by just moving stuff around. So I'm going to go ahead and undo the 3/4. Or actually, I'm going to divide by 10. So I'm going to get 6 over 10, which is then 3/5 equals 3/4 times that times dh dt. Now I undo this multiplication here, so I'm going to get 12. Nope. It's times 4/3 to undo that. That's going to cancel, so I'm going to get 4/5 equals the square root of 4/3 times dh dt, which means that dh dt is just 4 divided by 5 with this in the denominator as well, because I've got to divide by that. And that's a constant. That is the rate at which the water level is rising. So it's going to be 4, oops, I forgot my equal sign, equals 4 over 5 times the square root of 4/3. And our units, again, this is going to be, let's see, they said feet per second. And that was our last question. I know that I might not have done the best job at explaining this topic. I'm really not sure how to explain this topic, or how else to explain it for that matter. This is, quite frankly, one of my worst calculus topics, so if you're going to ask me more questions about it outside of watching this video, please don't be surprised if I'm not super helpful. It's just particularly difficult for me to put into words, but I really recommend writing out every single piece that you know and every piece that you don't know and need to know, and just write out all of your steps and keep track of all your steps so you don't lose anything. But yeah, so that was all of the questions for this one, which means this is all done, and I hope that this was helpful. Thank you for watching.